In this video we will present the Chinese remainder theorem. This theorem assures the fact that if we have k different moduli which are co-prime 2 by 2 and some reminders b1, b2, bk from an unknown x, x has a unique solution modulo m, where m is the product of all the moduli. Okay, in the first place we have to understand the difference between co-prime, to be co-prime some numbers, and to be 2 by 2 co-prime. So for example, if we would have 2, 5, 14, they are co-prime because there is no integer greater than 1 which will divide all these three numbers at a time. But they are not 2 by 2 co-prime, because if we would take 2 by 2, then these numbers 2 and 5 is okay, they are co-prime. 2 and 14 is not co-prime because their greatest common divisor is 2. So these three numbers are co-prime but are not 2 by 2 co-prime. So be careful to this aspect. Okay, so in our case, in the Chinese theorem remainder, we need the moduli to be 2 by 2 co-prime, and we will have an example here. We have the unknown x here, which is congruent to 1 modulo 4, congruent to 0 modulo 3, congruent to 7 modulo 5. As you can see here, there are 4 steps to do. In the first place, we have to check that the moduli are 2 by 2 co-prime. So 4, 3 and 5 are 2 by 2 co-prime, so this is checked. Next, we have to compute Ci, C1, C2, C3. Who is Ci? Ci represents the product of the other moduli. So, or in other words, we can say that Ci is the product m, the product of all the moduli, divided by the moduli mi. Okay? So, in this place, we will create a new intermediate, let's say, congruential equation, which is created in this way: Ci xi is congruent to bi modulo mi. So these are some intermediate congruences, and these congruences we would be interested to solve them, and in order to solve them we will transform this congruential equation in a Diophantine equation, which we already know how to solve it. So we will take one of these three Diophantine equations and we will solve it. As you can see here, this is the last Diophantine equation. We want to compute x3. We are not interested in computing y3 because due to the fact that we have congruential equation here, we only are interested to find x. So here are the steps which you already know. So in the first place we computed the Euclidean algorithm, then the extended Euclidean algorithm, we checked the result, then we computed x, and in our case x3 is 1. Next, we want to guess, let's say, who is x1. So we have 15 modulo 4. We reduce 15 due to the fact that 15 is greater than 4. So in Z4 we only have these numbers, and 15 modulo 4 is one of these numbers, and in our case is 15 is 3. Okay, so we will have 3x1 congruent to 1 modulo 4. So it is easy to try these possible solutions, and we find that x1 is 3 due to the fact that 3 times 3 is 9, and reducing it modulo 4 is 1. Somebody asked me how can we reduce modulo a number. So we will we have the number 9 and we want to reduce it modulo 4. So we will write 9 minus, and here will be the multiple of 4, so 4 times something, the multiple of 4 which is closest to 9 but is not greater than 9, so it is 8. So this will give us 1. If here we will have a very big number, we can divide this big number by the modulus. You can use for that computer, and we will get a number with some decimals. We will take this number and we will multiply the modulus by that number. Okay, so let's continue now. So x1 in our case will be 3, x2 will be 0, x3 will be 1. Then we are interested to find the final x. So the final x will be computed in this way. We will take all ci and xi. We will compute this sum, and do not forget to reduce the result modulo m. So in our case we have c1 x times x1 plus c2 times x2 plus c3 times x3. The result will be reduced modulo 60. And then we can check this. I already checked it and it is okay. So this is the way to apply the Chinese remainder theorem. I hope it is useful for you, and if it is, you can give a like to this video clip and subscribe for the next video clips. Good luck. Bye.